So in the last video, we saw that if we take a normal form game and we repeat it a finite number of times, the result is essentially boring in the sense that the subgame perfect equilibria are precisely playing some Nash equilibrium in every stage. So we don't get any new behaviors. So I hinted that we're going to get around this by repeating a game infinitely many times, in which case we get genuinely new behaviors like cooperation in prisoner's dilemma. But now we hit a problem, which is that to do this, we have to go outside of the formal definition of extensive form that I've given you. Because if we drew this as a tree, this would be an infinitely deep tree. It would just keep going. It would never reach a leaf. That's the point of an infinite play, is that we will never reach the end. We will always keep going. So one problem is that we can't just put payoffs at the leaves. So we generally get around this informally. We're not going to give a kind of, we're not going to extend extensive form to allow for infinitely deep trees. We're just going to informally say, we have a stage game and we're going to repeat it to infinity. So that means that a play of the stage game is going to be an infinite sequence of, a play in the infinitely repeated game is going to be an infinite sequence of moves of plays in the stage game. Okay, now there's another problem, which is previously I said in a finitely repeated game, we just add up the payoffs. But now we can't do that because we're adding together infinitely many things and the sum is going to diverge. Everything is going to be infinity and nothing will work. So we're going to get around this with a trick called discounting, which essentially means that the further into the future we go, the less the payoffs are going to count towards the total payoffs. So I'm going to say a few things about why we do this and what it could mean. So mathematically, what we're going to do is we're going to pick a number called the discount factor, and this is going to be a real number between 0 and 1. And the total payoffs for a player, so given X, which is a infinite sequence of plays, we're going to say that the total payoff is going to be this thing. So it's the sum from the first stage all the way to infinity of the individual stage payoffs. But in each one, we multiply by beta to the I, and because this is between 0 and 1, this gets smaller and smaller. So this is a geometric series, so this thing is always going to converge. So we're always going to get a finite value here. Okay, so there's a few perspectives on what it means to do discounting and pick a discount factor. So, I mean, one perspective which you can take is to say that this is a mere trick. We need this in order that we get a mathematically well-defined model and that we can say anything at all, and that's okay. But it is possible to do more and to say that the discount factor actually has some kind of game theoretic meaning. So a common perspective is that the discount factor is a kind of measure of the patience of the players. So if you're playing a repeated game, you might be impatient and you might prefer to get payoff now rather than having to wait a long time before you get payoff. So in this case, beta is a kind of measure of, so in this case, lower beta means you're more impatient. So if beta is very low if beta is very low, then you put much higher weight on immediate payoffs versus payoffs far in the future. If beta is close to 1, then you value payoffs in the future relatively much higher. And we can go further. There's no particular reason that we have to use the same discount factor for every player. It's just slightly convenient. So we can actually have different players with different kind of patience levels. An alternative perspective, which I quite like, is that beta is the probability that the game terminates at any given stage. So this is not really an infinitely repeated game. It's just a game whose end point isn't determined, and we have a kind of constant probability that we end on any given round. And in this case, this formula for the total payoff is exactly the expected payoff. So in this case, note that if this happens, then the game will eventually terminate with probability 1. The probability is 0 that this game keeps going forever. And I should say, this kind of geometric, so this is called geometric discounting because this is a geometric series. So we kind of multiply by it's multiplicative. We multiply by a factor of beta at every stage into the future. There are other things that we can do. We do a thing called limit of means. We can do a thing called hyperbolic discounting. There are some other options. I'm going to stick to geometric discounting basically because the maths is easier. And you're going to see that the maths gets kind of tricky even so. But these are much more of a headache. But some of these, I think, particularly hyperbolic discounting, there is some kind of behavioral experimental evidence that that this is closer to the way that humans reason. But I won't say any more about these. Okay. So now we have to say what are strategies for an infinitely repeated game. So a pure strategy for an infinitely repeated game is going to be a thing that tells them that for any finite list of the history of play that they could see up to their current stage, it's going to tell them what to do now in the next stage. So for example, if we have a 2-player game where player 1 has X set of moves X and player 2 has set of moves Y, then the set of pure strategies for player 1 is going to be the set of functions that input a list of pairs of an X and a Y and output an X. So this thing is the set of all lists, including the empty list. So if we input a list of length n, that's the strategy is going to tell us what we're going to do in stage n+1 if the history up to this point that the player sees was this. So in particular, this says what the player does in stage 1, where there's nothing to observe. There's no history so far. So for that, we input the empty list to the strategy. Okay, now the maths is going to start getting tricky. So let's work out an example of evaluating the total payoff from a pair of strategies for some player. So let's say we're going to play infinitely repeated prisoner's dilemma, and we're going to pick the discount factor 1/2. Now, player 1 strategy, so player 2 strategy is going to be always defect no matter what. That's a valid strategy that says, given an input history, ignore it and defect. Player 1 strategy is going to be a thing called grim trigger. I'm going to come back to kind of naming a lot of examples of strategies. So this is the first kind of interesting example of a repeated strategy that I'm showing you. So grim trigger says that if your opponent has never defected at any point, then cooperate, and then if they've ever defected, then defect. So what this means is that you kind of cooperate up until the first point where your opponent defects, and then after that you defect for all time. So grim trigger is kind of what it sounds like. It's you move into a kind of attack state and you stay there. In particular, this grim trigger initially cooperates because when we input the empty list, we will see that in the empty list, the opponent has never defected because they've never done anything. So initially, this thing will cooperate. That's crucial. Okay, now if we think about how these two strategies interact, we will see that in the first round, player 1 is going to cooperate because we input the empty list for the history and it says player 2 has never defected up until now, so we're going to cooperate. Player 2 strategy is always defect no matter what, so player 2 will defect in the first round. So in the first round, we play CD in the stage game. Now, after that, player 2 is, of course, going to defect, and player 1 is going to see that, yes, player 2 has defected, namely, they're going to defect in every round. So after the first round, player 1 is always going to see that player 2 has defected. So that means they're going to defect back. So what that means is that in all other rounds after the first one, the player is going to be defect. Okay, so now we have to do some maths. So if I plug the payoffs from these into the formula for the total payoffs, what we're going to see is that we're going to get the payoff from C. So we're going to work out the total payoff from player 2. So so player 2 here, so player 1 is the sucker in the first round. So player 2 is defecting, so they're going to get the higher payoff, which is 3. So we're going to get the payoff for player 2 from defecting against the sucker times 1 copy of the discount factor, which is 1/2. And then for stages 2 to infinity, we're going to have the payoff from defect times that many copies of the discount factor. So now you plug this in, this number here is 3, this number here is 1, so we get 3/2 plus this sum. Now, one way to do this, this is simple enough that you can just eyeball it. Think about shading a square. If you shade 1, so this sum is, if you think about what this is 1/4 plus 1/8 plus 1/16 plus 1/32 plus, and so on to infinity. So if you think about a square and you shade 1/4 plus 1/8 plus 1/16 and so on, if you think about this for a while, you'll see that the sum is exactly 1/2. You'll end up shading half of the square in the limit. So how you do this properly is with the reindexing trick, that you pull out a factor of 1/2, and then this allows you to reindex this sum, so it goes from 1 to infinity, because we have kind of an extra copy of 1/2 we're getting. And now at this point, we can apply the formula for the sum of an infinite geometric series, which tells us that the value of this thing is 1. So we end up with 3/2 plus 1/2, and we get a total payoff of 2.